In our last lecture, we were discussing about the various properties of the discrete Fourier transforms, and we had seen the properties related to the translation, the rotation, then the periodicity property, the conjugate symmetry property, how the average value is linked with the frequency component, that is to say the frequency component 0, 0. Okay, these are some of the things which we were seeing in the last class, and towards the end of the lecture we were discussing about the circular convolution, and the lecture basically remained incomplete. So we would basically start with that. Now, just for the benefit of the people who had little bit of difficulty in conceptualizing the concept of the circular convolution, okay, I will once again briefly tell you about the circular convolution operation and explain its physical concept, and then we will see that how the circular convolution can be computed using the discrete Fourier transforms. All right. Now, the expression which we had defined for the circular convolution is like this. We had the function, we had two functions, one is u1, okay, and the other function is h, okay, and the convolution, the circular convolution of these two functions are defined by this relation, okay. We choose some coordinates m prime, n prime. The coordinate system that is chosen is m prime, n prime, and on that we take a specific point mn, okay. Now, we have two functions basically, one is h of mn and the other is u of mn, okay. One is u1 of mn and the other function is h of mn, and we had the original coordinate system as mn, okay, and now we have gone over to a new coordinate system m prime, n prime, okay. And with respect to that, the definition of the circular convolution, okay, the mathematical definition is like this, okay. We have to take h, for the h function, we have to take m minus m prime, n minus m prime, okay, which is defined circularly, and the circular function definition is given here. A function h mn defined in the circular way is given by h m modulo capital N, n modulo capital N, okay. So, these indices m and n which are there in the function, they are just defined as the modulo n functions, very simply, okay. And the function which we are choosing for h is m minus m prime, n minus n prime, and the other function is u1 m prime, n prime. And the mathematical definition of convolution is that if we are taking this product and summing up, okay, over the space m prime, n prime, entire space of m prime, n prime, that is to say within the limit 0 to n minus 1 and 0 to n minus 1 for n prime, then we get a function, okay, which is called as the u2 function, okay, which is defined for the position mn. All right. Now, what are these mn's? These mn's are given as these indices. The mn's are coming as indices in this h function, okay. So, physically it means like this. We take a function h of mn. This was our original function definition, and we had chosen this function, okay, defined over the space capital M by capital M, okay, which I said was smaller than the space capital N by capital N, which was for the entire image, okay. The image function is taken as the function u1, okay, with indices mn. Even the h also is being defined originally with the indices mn, okay. And supposing the function which was defined, okay, is like this. The h function, the original h function definition, okay, is whatever is contained within this shaded box, okay. This shaded region indicates the h function, so that within this shaded region h of mn is not equal to 0 and outside this region h of mn is equal to 0. So this was our original h function, and the function u1 of mn was defined over the entire n by n array, whereas the function h of mn was defined over an m by m array. So this was m by m, whereas the image was for capital N by capital N. All right. Now, in this definition we have, okay, m minus m prime n minus n prime. So what we are doing, we are going over to the m prime n prime coordinate space. All right. And on that we are choosing a particular point mn, okay, and that particular point mn we are computing the convolution value, okay. And exactly what does it mean? The function that we are choosing is m minus m prime n minus n prime. These are the indices for h. Now assuming that, if you assume that m and n, that m and n is chosen to be the point 0 0, okay, then we would have simply got it as h of minus m prime minus n prime, okay, and that would have meant, okay, the following. If we choose an m prime n prime coordinate system over here, then choosing the function as h of minus m prime and minus n prime would have meant that we would have taken a simple image, okay, of the function, rather a folding of the function, okay, in the negative region. That is to say, if this shaded region were folded, okay, about this mn coordinate space, okay, we would have got a function, okay, like this, which would have been our h of minus m prime minus n prime function, okay, and we are just translating this function to the point mn, okay. If we apply a translation of mn, okay, to the function h of minus m prime minus n prime, that is to say, we are applying a translation on that folded function, okay, and giving it a translation of m and n. So after translating, we will be getting the function as h of m minus m prime n minus n prime, okay. So this function is now defined with respect to this mn point, okay. And the circular convolution definition, again we go back to the definition of the circular convolution, okay, which says firstly that this m and m minus m prime n minus n prime, those are modulo n indices. That is the first definition because of the circular function, okay. And what we are simply doing, we are simply multiplying this function, okay, by u1 function, the image function, okay, whose indices are m prime n prime, and this we are integrating over m prime equal to 0, n prime equal to 0 to n minus 1. Both m prime and n prime defined over 0 to n minus 1. So that means to say that with the h function defined like this in this zone, okay, we are just making a point by point multiplication, okay. The multiplication of this point with the h, this point with the h, everywhere all over the image it is a multiplication of this function with this h of mn function, okay. Now the question is that this h of m minus m prime n minus n prime is circularly defined. So as a result of that, the region, okay, which is going out of the positive m prime and positive n prime axis, okay, the region which is going out of positive n prime region, that is to say the region which is not in the first quadrant, okay, will simply get folded over, okay, to the other parts of the image. So whatever shaded area we had over here, that came in this region. Whatever shaded, this green shaded region we had here came over this zone. Whatever we had at the black shaded region came on this zone, okay. And it is a simple point by point multiplication. At these points we don't have the h function defined, that means to say the h function is equal to 0, whereas in all these 4 shaded parts, okay, the h function is not equal to 0. So if we are doing a multiplication like this, okay, over the entire m prime n prime space, then what are we getting? We are computing the function, the convolution function u2, but defined at which point? Defined at the point mn only, alright. So by doing this n by n, that is to say n square computation, this function u2 is computed only at one particular point. Now if you want to have a convolution, okay, over the entire image, okay, what you have to do? You have to compute this u2 mn for the entire image space. That means to say for the entire m equal to 0 to n minus 1, n equal to 0 to n minus 1 space. And that means to say that this particular function, okay, which you had defined over here, you have to position this function, okay, one by one to all the points in this image. At this, when it is positioned at mn, you compute only u2 mn. When it is positioned at 0, 0, you compute u2 0, 0. When it is positioned at 0, 1, you compute u2 0, 1. Like this, from u1, from u2 0, 0 up to u2 n minus 1, n minus 1, at all the points individually, you position this two-dimensional function h, okay, and get this convolution. If you are doing that, then you will get the convolved array u2 mn, okay. So this is the concept of circular convolution, okay. Is the point very clear with you, okay, or still any further confusion? All right. I mean, if it is clear to you, then we can proceed further that how are we going to compute this expression, because as I told you that in order to compute this, now what I have to do, this n square number of multiplications, okay, which are defined over here, I have to do for all the n square number of points, okay. Now, is there any simpler technique of computation, okay? So for that matter, what we will investigate, that rather than doing this convolution in the spatial domain, this is of course in the spatial domain because m and n are defined in the spatial axis, okay. If we go over to the transform domain, that is to say instead of mn space, we go over to the kl space, then whether we get any computational advantage or not, okay. This is what we are going to study today, okay. So what we do, we simply define the two-dimensional DFT, all right, for the function h. So we are choosing the function h of m minus m prime, okay, n minus n prime, and we are indicating this with the suffix c, all right, where the suffix c simply stands for a circularly defined function, all right. Then now let us take a 2D discrete Fourier transform of this function, okay. Now what is the 2D DFT of this function? Can you tell me? Okay, h of m minus m prime, okay, n minus n prime, and I am going to compute the 2D DFT, okay, for a fixed m prime n prime, okay. That means to say that the indices of the DFT which I am going to have, okay, that is defined for mn, okay. So for a fixed m prime and n prime, what is the 2D discrete Fourier transform of this? Can you tell me? This is the h function. This is to be multiplied by what? The w term to the base capital N, because there are capital N number of points, okay, and I mean capital N is the length of the sequence, and this is raised to the power mk plus nl, okay, mk plus nl, where k and l are the indices in the frequency domain, okay, and m and n are the indices in the spatial domain, and this double summation is defined over which space? Simply m equal to 0 to n minus 1 and n equal to 0 to n minus 1. Okay, this is the two-dimensional discrete Fourier transform. All right. Now I have little bit of a problem, okay, about this function. Okay, the thing is that here I have the indices as m minus m prime, n minus n prime, whereas for the complex exponential term, its power is mk plus nl. Okay, in order to make it compatible, what I should do? I should raise it to the power of m minus m prime into k plus n minus n prime into l. So that because it is fixed m prime n prime, okay, I will take the m prime w to the base n, m prime n prime terms outside. Okay. So see what I do, I will simply take w to the base n, okay, m prime k plus n prime l, this term I take outside, okay, and within the summation I get summation m is equal to 0 to n minus 1, summation n equal to 0 to capital N minus 1, h of m minus m prime, sorry, comma, n minus n prime, okay, multiplied by w to the base n, what? m minus m prime k plus n minus n prime l. All right, m minus m prime k plus n minus n prime l. Okay, this is what I get. Okay, now let us write m minus m prime as I and n minus n prime as j. Okay, I define I as m minus m prime, j as n minus n prime. So simply what I get, okay, from this is, then this expression becomes equal to w to the base n m prime k plus n prime l, okay, summation over I and j, all right, h of I j w to the base n, okay, I k plus j l. Is that correct? What is going to be the limits of I and j? No, minus m prime, because I am making the substitution I is equal to m minus m prime and j is equal to n minus n prime, so that when m is equal to 0, I is equal to minus m prime, okay, and j is equal to minus n prime. Okay, so I equal to minus m prime to, this becomes the top limit becomes n minus 1 minus m prime, and for j it varies from minus n prime to n minus 1 minus n prime. All right. So that is how the limits are there for this hij function. Okay, because of my definition of ij, okay, this is what I get. All right. Now, is this whatever I have written here, is this the discrete Fourier transform of hij? Well, I mean it is, but let us see further how. There is a little bit of problem in the sense that my limits for the DFT expression is defined. I mean, had this been a DFT, it would have been I is equal to 0 to n minus 1, j is equal to 0 to n minus 1. But in this case I am having I equal to minus m prime to n minus 1 minus m prime, and j is equal to minus n prime to n minus 1 minus n prime. So it is not 0 to n minus 1 limits. But do you think still I can call it as DFT? Why?
Circular indifferential.
Yes, excellent. The correct answer is that my h function is defined as a circular function. Okay, and that is why whenever I have I equal to minus m prime to n minus 1 minus m prime, okay, in the modulo n terms, it will be meaning I is equal to 0 to n minus 1, and the limits of this would have been j is equal to 0 to n minus 1. So simply by the circular function definition, okay, I can write this as w to the base n m prime k plus n prime l, okay, summation, double summation rather, I is equal to 0 to n minus 1, j equal to 0 to n minus 1, h of I j, okay, w to the base n I k plus j l, and now this expression, okay, what I encircle over here, okay, this expression is our pure and simple 2D DFT, okay, 2D DFT of what? 2D DFT of H, okay. So, it is w to the base n m prime k plus n prime l, okay, this multiplied by simply DFT of H I j, okay, or rather I can call it as DFT of H mn also, okay, because whether I choose indices I j or mn, to the base n, all right, okay. This multiplied by, there is an extra term coming over here, okay, because my original DFT which I was choosing was not on H of mn, but it was the DFT of m minus m prime, n minus n prime which I have done, okay, and the result of that is I got the DFT of H mn multiplied by this extra term concerning m prime k and n prime k l, all right. Now, I go back to the original definition of the convolution function u2 mn is equal to this, and in this expression simply what I do is I take the discrete Fourier transform, okay, of both the sides, okay, the left hand side as well as the right hand side, I take the discrete Fourier transform, okay, and with indices mn, all right. So that the left hand side, which is simply u2 of mn, okay, will simply become, okay, taking DFT of both the sides of the convolution expression, okay. The convolution expression is whatever is defined in the last class, okay. What I have on the left hand side is simply DFT of u2 mn, okay. Of course, it is a DFT with a base capital N, okay. And what is that? What is the right hand side? Please apply the definition over here that 2D DFT of H minus m prime, H of m minus m prime, n minus n prime has been already obtained like this, okay. You need in your definition, in the definition, I mean in the convolution function definition, we had two functions, okay, H of m minus m prime, n minus n prime, and u1 of m prime n prime, okay. So, with respect to mn, the DFT that we are taking is on this function, okay, on this circular function H of m minus m prime, n minus n prime, and DFT of this, okay, and this function remains as before, okay, and the DFT of this is simply DFT of HMN, okay, with the term Wn Wn m prime k plus n prime l, okay, remaining outside, okay. So, we get a term, okay, w to the base n m prime k plus n prime l, okay, that term was outside, okay, and we get the function u1 m prime n prime also outside, okay, and the remaining term becomes simply DFT of HMN, okay, and this term u1 of m prime n prime and multiplied by w to the base n m prime k plus n prime l, okay, with summation m equal to 0 to n minus 1 n prime is equal to 0 to n minus 1, what does that result? Okay. Let me, just explain, because, let us write down the things mathematically, then it will be more clear. This I can write as dft of h m minus m prime n minus n prime, okay, circularly defined, okay, and then I have this product with a double summation m prime is equal to 0 to n minus 1. Rather, my entire term should have been with this double summation m prime is equal to 0 to n minus 1, n prime is equal to 0 to n minus 1, dft of this, okay, and then u1 m prime n prime, okay, and this I can simply write as dft of hmn, okay, and then I have summation m prime equal to 0 to n minus 1, summation n prime equal to 0 to n minus 1, u1 m prime n prime, okay, w to the base n, what is the term that is left out? M prime k plus n prime l. Now tell me, what is this expression? This is the DFT of u1. Okay, this is very simply the DFT of u1. So that what I have over here is DFT of hmn, okay, of course to the base capital N, multiplied by DFT of u1 mn, okay, to the base n. So what is the physical conclusion? Convolution in the spatial domain. This is how I had defined a convolution in the spatial domain, alright, and that becomes a multiplication in the frequency domain. That means to say, when I take the DFT, okay, of a convolution signal, it is the product of the DFTs of the functions which are involved in the convolution. So DFT of this simply becomes a product of DFT HMN, DFT U1 MN. Okay, that means to say it's a very important property. Okay, it is there in one-dimensional convolution also, and in this case we are doing a two-dimensional convolution. For a two-dimensional convolution, the important property is that the discrete Fourier transform, okay, of the convolution in the spatial domain is a multiplication in the frequency domain. And look at this, okay, the DFT of these expressions can be computed very efficiently using the first Fourier transform operations, using n log n number of operations, alright. So DFT of this and DFT of this can be individually computed using the FFT algorithm, okay, and then you take their product and take the inverse discrete Fourier transform of this, okay. If you take inverse discrete Fourier transform of DFT U2 Mn to the base n, you get the original sequence U2 Mn, which is the convolved sequence. You get the convolved sequence U2 Mn, okay, by simply carrying out the inverse discrete Fourier transform, and even the inverse discrete Fourier transform can be computed using the first Fourier transform algorithm, because inverse DFT simply means the multiplication factor w to the base n, okay, instead of that being mk plus nl, it becomes minus mk minus nl in the case of the inverse DFT, alright. So this entire convolution, okay, can be computed, okay, very efficiently using the first Fourier transform algorithm, okay. So this is what we mean by the convolution property, okay, of the discrete Fourier transform. So that was the last property, or rather if I remember correctly, it was the property number 8, okay, which we studied in our discrete Fourier transform. Any questions? Any difficulties? Okay. before we introduce the new concept?
In this expression, this first top one is actually mathematically correct. Can you take DFT of that one outside?
No. I mean, as I told you, I mean, while writing itself, I wanted you to make this correction. Basically, this is it should have been written in this form. Double summation U1 m prime n prime DFT of h of m minus n prime n minus n prime circularly defined. Okay, and then when this results in h of mn into DFT of h of mn into wn to the base w to the base n m prime k plus n prime n, in the second step you can take the DFT outside because m prime n prime are no longer there. So this HMN you can take out that time. Okay, so in the first step I should have written the double summation first and then this function. All right. Okay, so now let us go over to the new topic. Okay, now one thing which you see in our discrete Fourier transform expression is that the transformation, the elements of the transformation matrix, okay, which we are defining, okay, that is what? W to the base n mk plus nl. Okay, these are the elements of the elements of the transformation matrix which we got, okay, in the DFT expression. And what is W to the base n? W to the base n is nothing but exponential to the power minus j 2 pi by capital N. So W to the base n itself is a complex expression. So the matrix elements which we have are all complex elements. All right. The multiplications which we are doing, okay, in the DFT operation, they are all complex multiplication. And as you know, every complex multiplication is equivalent to 4 real multiplications, because whenever I am trying to compute a plus jb into c plus jd, this means to say I am computing 4 real multiplication ac minus bd plus j of bc plus ad. So totally 1, 2, 3, 4 real multiplications get involved. So this is what we are having over here, that every multiplication is complex. Now the question is it possible to define a unitary transformation, okay, where the elements of the transformation matrix, instead of being complex, okay, are all real? It is possible to define such unitary matrices, okay, and with that concept, okay, the transformation technique which will be presented now, that is called as the discrete cosine transform. Okay. So we now introduce the discrete cosine transform. In short form, this is written as DCT. That was called as DFT, and discrete cosine transform is known as DCT. Okay. And if we define the transformation matrix C having elements C of Kn, okay, that is to say for one dimensional transformation. I first considered the one dimensional transformation only, that is to say my same old expression. What was the old transformation expression? Vk, okay, or rather the V vector equals to A matrix, transformation matrix product U vector, okay, or I was writing this as, this implied Vk equal to summation A k n, okay, Un, okay. This is what I had got for n equal to 0 to n minus 1, and this was defined for k is equal to 0, 1, etc., up to n minus 1. This was my original expression. Now this C of Kn, okay, the elements of this transformation matrix, instead of calling it A, I am calling it as C, just because it is a cosine transformation, I indicate it by C. Okay. Now, the definition of the elements is simply this: Ckn, okay, is equal to 1 upon square root of n. Okay, the square root of n factor, you know why it is coming, because I defined that in the case of unitary DFT, unitary one-dimensional DFT, we were having the factor 1 by square root of n coming. Okay. So, very similarly 1 upon square root of n, okay, in order to preserve the unitary property, but this is for k equal to 0, okay, and n defined for 0 to capital N minus 1, okay. 1 by square root of n for k is equal to 0 and n varying from 0 to n minus 1. So, what does this mean in the matrix space? It means that the first row. So, please note that all the elements in the first row, which is indexed by k equal to 0, are equal, and that is equal to what? Equal to 1 by square root of n. Okay. Second row onwards, okay, that means to say when k varies from 1 to n minus 1, the term is like this. It is square root of 2 by n, okay, entire square root 2 by n, okay, cosine of pi 2n plus 1 k divided by 2n, okay, where k is defined for 1 to n minus 1 and n is defined as before 0 to capital N minus 1. So, these are the element values, okay, when, okay, I will just dictate what it is, okay. Ckn is equal to square root of 2 by capital N, square root of 2 by capital N, square root of entire 2 by capital N, cosine of numerator is pi 2n plus 1, 2n plus 1 written within parenthesis, pi within parenthesis 2n plus 1 multiplied by k, okay, and the denominator of the cosine argument is 2n, okay. So, pi 2n plus 1 into k by 2n, this forms the argument of the cosine function, and this is defined for k within range of 1 to n minus 1 and n within the range 0 to n minus 1, okay. So, these are the elements of the cosine transformation matrix. So, what do you find? Okay. You simply find that the elements are all real elements, okay. So, I can quickly write down the properties of this, okay. So, the properties that I find from the definition itself, okay, properties of DCT, okay, that first is that it is real and orthogonal, meaning C is equal to C transpose, because it is real, C is equal to C transpose because all the elements are real, okay. And another property is that C inverse is equal to C transpose, okay. The inverse is equal to transpose, okay, because it follows the orthogonality property, okay. Then I think many of us, okay, have got a misconcept that if you take the discrete Fourier transform, the discrete Fourier transform expression, okay, has got the real part as well as the imaginary part. Each DFT transformation matrix element has got a real part and an imaginary part. So, many people tend to think that take the real parts only and then it becomes the cosine transform, okay. Just because cosine happens to be the real part of exponential, many people have got a misconception that it is that. But do you find that the definition which I have written, okay, is it the real part of the unitary DFT? Is it the real part of the unitary DFT? No, it is not. Okay. So, the discrete cosine transform is separately defined. Okay. So, it is important to note here that the DCT is not the real part of unitary DFT. All right. Now, from this kind of a definition for the transformation, okay, it is quite easy to see that we can apply a fast algorithm for its computation. All right, because again the fast algorithm application concept is that you keep on dividing the original sequence into several smaller subsequences and do the elementary discrete cosine transform operation, and this you can do even here also. So, the algorithm is fast implementable using the FFT operation, and mind you, you get an advantage over here because in FFT the n log n operations which you were doing were all complex operations, okay, whereas in this case all of them are real operations only. It is n log n but real computations, not complex. Okay. So, the DCT is a first transform with computational complexity order of n log to the base 2n, okay, and all these are real computations, not complex as in the case of DFT. All right. And the fourth property, okay, which makes the DCT very useful, okay, is that the DCT has excellent energy compaction. Energy compaction property. What is meant by energy compaction? That means to say that that in the transform domain, okay, the energy is contributed by only a few samples in the transform domain. Okay, so it has got an excellent energy compaction property. So this can be used, okay, very effectively in data compression, image data compression applications. Okay. The other things are quite similar to the FFT. So, I am not going into further details of this. The basic kernel you find here, they are all the cosine functions. Okay. The basic transformation is a cosine functional transformation that is taking place. So, we have undoubtedly simplified our computational process. Instead of complex elements, we have already come down to real elements and simplified our computation. But mind you, we are working in the digital domain. Okay. So, obviously, we are trying to simplify our computation further and further. Even in this transformation, what we find is that you have to keep on computing in order to form the transformation matrix, you have to keep on computing the cosine values, and all those cosine values will be some real values, okay, which are to be computed individually, okay, and all those real values are to be multiplied by the appropriate UMN samples in order to compute the VKLs, that is to say the transformed image. But instead, is it possible, okay, to suggest or devise a transformation where the elements are purely binary? If we can do that, then definitely we are going to make the computational complexity even smaller. Okay, we are going to make our computations even smaller, and that too just imagine a case that you define a matrix, transformation matrix, where the elements are +1 and -1. If you can do that, just think of it, you are entirely saving the multiplication operation. Then the entire transformation becomes a set of additions and subtractions. Okay. So now our objective will be to define a transformation matrix where the elements are not only real, but they are binary elements and the elements are just +1 and -1. So with this objective in mind, the transformation that is proposed, okay, is called as the Hadamard, Hadamard, okay, named after the person who suggested this, Hadamard transform. Okay, and mind you, the Hadamard transform is defined with respect to a very elementary matrix. What is the elementary matrix, smallest elementary matrix that you can think of? It is a 2 by 2 matrix that you think of, and Hadamard transform just defines a 2 by 2 matrix, believe it or not. They just define a 2 by 2 matrix, okay, from which you can compose any n by n matrix, not any n by n, rather when n is a 2 to the power of n, okay, 2 to the power of any integer, okay, then of that size, any Hadamard matrix you can compose out of the elementary matrix which I am presenting now. That elementary matrix definition is, okay, the elements of that is 1, 1, 1, and this element is -1. Okay, this element, this last element is -1, rest of the elements 1, 1, and 1. Now it is a 2 by 2 matrix, and again, since this has to be a unitary matrix, this is to be normalized by, an n by n matrix is normalized by 1 by square root of n. So a 2 by 2 matrix is to be normalized by 1 by square root of 2. So this is the elementary matrix that is defined. What do you find simply from this elementary matrix? First is H1 is equal to H1 star, very simply because it's a real matrix. Then H1 and H1 transpose are also equal, okay, and H1 is equal to H1 transpose, and that is same as H1 inverse. Okay, so the matrix which is now formed, okay, is symmetric, it's real, okay, and it's orthogonal. All right. So this is the elementary matrix, and the matrix of higher size can be composed by simply using this elementary matrix. I will tell you how. This is a 2 by 2 matrix. Now, if I want to compose a 4 by 4 Hadamard matrix, what I will do is, I will define the 4 by 4 Hadamard matrix as H2, alright, and that will be, that is to say 2 is the dimension, so 2 rows and 2 columns, or rather of size 4, so that I will get totally 4 rows and 4 columns, sorry. So H of 2 will be defined as the Kronecker product of 2 H1s, simply. So can you tell me, if I take the Kronecker product of H1 with H1, okay, what does that result?
4 by 4.
I get the multiplication factor as 1 by root 2 square, that means to say it becomes half, okay. And what are the elements of this Kronecker, I mean after doing the Kronecker product, just tell me the block matrix form.
1, 1, 1.
H1,
H1 minus H1, okay, in the block matrix notation. And H1 and minus H1, all of them are individually matrices. So it's in the block matrix form. So now simply what I have to do is, okay, in order to write it in terms of the elements, I will write the factor as half, alright, and I will write the H1 matrices in all these 4 subparts. Okay, what is it that I am going to write in the first subpart? H1. So H1 means 1, 1, 1, minus 1. What is this H1? Same, 1, 1, 1, minus 1. 1, 1, 1, minus 1, because even here also it is H1. And in last quadrant, here, the elements will be the elements of minus H1 matrix. So that means to say, minus 1, minus 1, minus 1, and here plus 1. Okay. So what I get as a result is the H2 matrix or Hadamard matrix of second order. This is the Hadamard matrix of second order. Alright. If I want to compose the Hadamard matrix of third order, okay, that means to say an 8 by 8 matrix. Okay. If I want to compose, okay, then can you tell me what will be the composition of this matrix? The first comes the normalizing factor, 1 by root 2 cube. Okay. And what are the elements of the Kronecker matrix, rather after forming the Kronecker product? Because simply what you will do as H3 is H2 Kronecker product with H1. Or rather it is same as writing H1 Kronecker product with H1, again Kronecker product with H1. Okay. Rather than that, because Kronecker product of H1 with H1 itself is H2, it is H2 Kronecker product with H1. Alright. So, what do we get in these elements? Simply H2, H2, H2 and minus H2. H2 matrix is known to me now. So, what I will simply do? I will write down the elements of the H2 matrix. So, I get H3 as, alright, 1 upon root 2 cube, okay, and you can yourself try. I mean, by the time I complete it, I suggest that you also try and you can verify whether your results and the results which I am writing are the same. Simply H2, H2, H2 minus of H2. Please write, substitute H2 here, H2 here, H2 here and minus H2 over here. Okay. So, what you get is, just verify with what I am writing. And in this case, it is minus H2. So this is what the composition of H3 matrix is, and in general the Hadamard matrix of order n, okay, is composed by what? It is Kronecker product of H of n minus 1 and H1. Alright. So that the basic composition is, it is 1 by root 2 to the power n over here, and this is H n minus 1, H n minus 1, H n minus 1 and minus H n minus 1. Okay. So this is the composition of the Hadamard matrix, okay, of order 3. Okay. Now we will take this Hadamard matrix of order 3 in the next class, okay, and we will see some further interesting things related to this matrix. All right. Any questions? Thank you.